So thank you again for the invitation, for the opportunity to do this. It's been a lot of fun. Thanks y'all for coming. So this is the last talk. So the aim today is at two of the applications of this technology of spectral networks to, on the one hand, to Donaldson-Thomas invariants or enumerative invariants. So some kind of new counting problems that come naturally from this notion of spectral network. And the other is to hyperkähler geometry of moduli of Higgs bundles. So that's the goal. Let me remind you where we are. What I tried to do in the first two lectures. So we started out with some data. The data we started with was a compact Riemann surface, C, an integer, and a tuple of differentials, say phi 2 up to phi n. Okay, the case n equals 1 is always trivial. I may as well just say n is greater than or equal to 2. Right, the notes. We have to repost the link because people
I will repost
otherwise
it.
don't.
Okay.
Okay.
I will repost
it. So we started with this data, together with some less important data, a spin structure on the Riemann surface and a complex CP1 structure on the Riemann surface. And from that data, we built some kind of derived objects. First, a rank n local system, which we wrote L H bar phi, but for short just L over C. And the way we thought of this local system, the way we got it was it's the local solutions. So this local system on a small patch, what it is the local solutions of well, it's a order n scalar ODE. We formulated it more precisely last time, but maybe this time we'll just say an order n scalar ODE, for example, a Schrodinger equation when n is 2. So just given the data of the surface and the differentials, we had this equation which we wanted to study. And then the tool that we were using to study it was first this spectral network, which we introduced in the first talk. And it depended on the data of a phase, which we usually take to be the argument of H bar, and this phi. And then the crucial thing that we discussed doing last time, and in general, this depends on conjectures. So almost always, this depends on conjectures, except in particularly nice n equals 2 cases. We used exact WKB and Borel summation to produce a rank 1 local system, which I called A for abelian, which was not over the surface C, but over the spectral cover. Which was an n-to-1 branched cover over C. So the very schematic picture of what we did is we wanted to study down here on the base curve C this local system GLN local system L. And what we described how to do is to replace it by a GL1 local system A over the cover. And the procedure was essentially to write down some ansatz for solutions of the equation and then use Borel summation to turn them into to actual solutions, and then do some kind of patching across the walls of the spectral network or Stokes graph. Okay, so this situation that we've arrived at of having two local systems that are related to one another, even though from exact WKB, we sort of formulated it in the language of exact WKB, you can describe the relation between these things kind of more simply than the way we derived it. And so I want to first say, what is the relation between, what is exactly the relation between the A upstairs and the L downstairs? So how to describe the relation between L without mentioning sort of complicated things like, OPERs and exact WKB and so on. There's just a purely topological construction that relates them. And I want to kind of indicate that construction. And maybe I should say, I should definitely say that, so I'm going to describe this kind of roughly in this lecture in the specific case of GLN. But recently there has appeared in work of Matei Ionita and Benedict Morrissey a kind of more professional account of this in the case of not only GLN, but for an arbitrary group. So I refer you to that.
Arbitrary reductive algebraic group.
Thank you. Yeah, but still, maybe it's useful to give you some account of how this thing goes for GLN. So, so what's the basic idea? The basic idea is that we're going to relate them by doing kind of the dual thing. We're going to take given a path on L, we're going to relate it to a bunch of paths. Sorry, given a path on C, given a path downstairs, we're going to compute its parallel transport in terms of paths up on the surface sigma. So what we want is a way of we want to lift paths from the base surface C to the covering surface sigma. And right away, there's a kind of obvious problem with trying to do this. And the problem is that the usual idea of path lifting over a branched cover is not a homotopy invariant process. So let me see what I mean by that. If we have, let me draw a picture of a little region of this cover, and I'll draw it in my usual way by giving, so this is a region on the base, and I'm depicting the cover as literally trivialized away from the branch locus. So let's say I'm just in the case n equals 2, so I just have this 2-sheeted cover with a branch point. Now, if I take a path that goes this way, I can lift that path to the cover, right? It has 2 lifts. I could call them the lift to sheet 1 and sheet 2. That homotopic to another path this path. So on the base, those 2 paths are perfectly homotopic. On the other hand, if I lift them to the cover, their lifts will not be the same, right? For example, this one has a lift. Let me indicate this even more explicitly. The first path would lift to two paths on the cover, which I could represent like this. There's the path on sheet 1, beginning and ending on sheet 1, and there's on sheet 2. Now, on the other hand, my second path here, if I lift it to the cover, well, it again has two lifts, but one of them begins on sheet 1 and ends on sheet 2 because it goes across this cut. And the other one begins on sheet 2 and ends on sheet 1 because it crosses this cut. So you have two paths which are homotopic downstairs, but their lifts to the cover taken naively are not homotopic upstairs. So this path lifting naively is not homotopy invariant, but we can fix it using the data of the spectral network, and that'll turn out to be the kind of key topological device. So to formulate that, I need to introduce just a little bit of notation to formulate carefully what this thing is. So I just want a language in which I can talk about kind of formal linear combinations of paths. So to say it exactly, and we could just be in the language of like topological spaces. Suppose I have a topological space and a subset. I mean, you should think of them as being like surfaces. So it'll be a surface and the subset of the surface, which is the whole surface except for the walls. And then we could consider the set of all paths in X with endpoints in Y. So it'll be the category of paths in X with endpoints in Y, but enriched over abelian groups. So all I mean by that is that if I have 2 points, the Hom from Y to Y prime is the abelian group of formal Z linear combinations of paths from Y to Y prime in the space X. Okay, so that's some kind of category, right? If I have 2 points, a morphism, so the objects are just the points of Y, and the morphisms are just formal linear combinations of paths from X to Y. And then, so that'll be my picture downstairs on the base curve. I'll just consider formal linear combinations of paths on the base curve. And then we have a covering. So suppose I have a map from Z to X. Then I can consider paths in the cover. I'll call it path Z from XY. So that'll be the category of paths now in Z. So paths on the cover with endpoints. So now the endpoints have to be in pi inverse of Y. So now the Hom from Y to Y prime is, again, an abelian group. It'll be formal Z linear combinations of paths, which now go from any preimage of Y to any preimage of Y prime. And now the composition. So when I looked at paths downstairs, I just took the most obvious composition rule, kind of extended bilinearly to these Z linear combinations of paths. Now here upstairs, I might have paths that don't begin and end at the same place. And so I'll just say the combination is 0 for paths that don't concatenate. So maybe I better draw an example of what I mean by this. So for example, suppose I have on the base curve, I have say, these 3 points. And then on the covering, I have, say I just have a 2-to-1 covering. So each one has 2 preimages like this. And so I could consider, say, so here's y prime, and y double prime. And a hom from y to y prime might be something like this. It could be a path. Let's say, here's a path A. And a hom from y prime to y double prime, well, I have, for example, this one I'll call B, and this one I'll call C. And then in my category, I'm allowing formal linear combinations of paths, so I could write things like 3 times A, and I compose it with 4 times B plus 7 times C. And then what I get here, A times B, I just say is 0. And I just get 21 AC, the concatenated path. Okay. That was probably a little more formal than I really needed. All I want to say is we're going to have some calculus where we consider formal linear combinations of paths, both downstairs and upstairs. And now, so now the statement is proposition. So in the good case where the spectral network is finite, remember, we drew a bunch of pictures of these spectral networks, and in favorable cases, they're finite. So let's stick to the favorable case where they're finite. Then there exists a functor from the category downstairs to the category upstairs. So paths on C, where the endpoint is not allowed to be on the spectral network, but other than that, they're just paths on C. And maps them to paths on the cover, formulated in this way. So paths on the cover, where again, the projection of the endpoints has to be away from the spectral network, with the crucial property of being homotopy invariant. So well, okay, there's a tricky sign in the story. So I'll call it almost homotopy invariant. Should probably just think it's literally homotopy invariant, but I don't want to lie to you. So let me say it precisely. So, so if I have 2 paths downstairs that are homotopic, then their images upstairs are almost homotopic. And what almost homotopic means is that when we homotope a path across one of the branch points of the covering, that path gets multiplied by a sign, -1. We pick up a factor -1. But up to that detail, this is going to be a homotopy invariant operation. And then you could ask, okay, how is it going to be constructed? Yeah, sorry, is there a question?
Yeah, I have a question. Just I was looking at your earlier lectures, but maybe I missed something. Is W generically non-finite?
It depends on what you mean by generic. So if we just take quadratic, if we take the case n equals 2 of quadratic differentials.
No, n equals 2 is not interesting. N equals 3. Do you get generically non-finite thing?
Then I think in a kind of random example, it'll typically be infinite. Yeah. Now, there are some special examples, like simple enough examples, like, polynomial equation in the plane for low enough degrees where it's finite. Okay. But indeed, it's typically infinite. Then there's a question: how do you extend this to the infinite situation?
So that's what we're complaining. Yeah. Okay. Sorry.
Right. So it's going to be almost homotopian invariant is the first thing. And then the second thing is that how concretely is it constructed? So given a path P, how do I describe what its lift is? So the statement all terms in f of P are obtained by a kind of splicing into the lifts. So I'm going to write the words which are defined in the notes. So I'll say they're obtained by splicing some specific curves, which are called WKB solitons with phase theta into the lifts of P. But rather than define right now what I mean by WKB solitons, I'll just show you the two sort of most important examples from which you can kind of see how it goes in general. So the most fundamental and important example is this one. So it's the situation where I have a branch point, and so this could already be in the n equals 2 example. We could have this, and now I draw in the spectral network, Stokes graph, and let me label it. The sheet labels 1, 2, 2, 1, 2, 1. And now I'm going to copy this a few times. So now suppose I have this path. Suppose I have this path P, and I want to describe how it lifts to the cover. So the kind of naive lift involved just 2 lifts, right, which we drew before. So lift on sheet 1, lift on sheet 2. So let me call this path Q1. And this path Q2. So those are the lifts to the double cover. And now the rule is that we have to include one more guy, one more path. And the way you can think of that path is that we travel right up to the Stokes curve. And then exactly when we get to the Stokes curve, we take a detour, we travel to the branch point and come back, but now on the opposite sheet. And if the Stokes curve is labeled 1, 2 like this, then we start on sheet 1 and end up on sheet 2. And I'll call that path Q3. That's what we call a detour path. So in this example, f of P will be just the sum of these 3 paths, Q1 plus Q2 plus Q3. Okay, so that's how this game works. We take all this kind of naive lifts that we had before, but then in addition, when we cross the lines of the spectral network, we splice in some additional kind of detours. And once you do that, I was include exercises. So here's a little exercise which you can really do, and I think it's helpful if you want to understand this thing. The exercise is to check. So let me draw a second path here. Call it P prime. So the check is that f of P prime is actually homotopic in this almost, so including these twisted signs, that's actually homotopic to f of P, to the sum of these 3 paths which I drew here. And that's the thing which did not work before without the detours. It does work here, so you have to sum up all the detours and see how they reproduce this this answer. But that's somehow the crucial property. Let me draw another example of this splicing.
Sorry, are there plus signs between these 3 terms on right-hand side?
Yes, these 3 all have plus signs.
This is linear
but of course,
combination, yes? This is
that's right.
linear
That's right.
combination.
It's a Z linear combination where in this case, all the coefficients are +1, right? That's what I said. So we're going to take kind of formal linear combinations of paths. And so this is an example of a formal linear combination where all the coefficients are +1.
Thank you.
Right. Right. But one of the important properties of this rule is that because it's completely local, it is compatible with the composition. In other words, it'll actually be a functor. If I have two paths and I compose them, I get the same. If I apply f to the composed path, I get the same as composing f of the two short paths. Okay, so one other example of splicing. Is the following. So let me draw sort of just a slightly more intricate picture. Where now I have, so now I'll be in n equals 3, at least n equals 3.
Hi, Andy. Sorry to interrupt.
Yes.
In the last exercise for the path P prime, since it passed through like the two of the network lines, would you have like more than 3 terms then?
Yes, absolutely. So you have to separately include the detours at the 2 points. So the idea is, right, f of P prime, because of this locality that I just told you, you can think of it as being broken up into 2 short paths, each of which crosses exactly one of these lines. And then the rule for each of those short paths is exactly as before. So each one of those has 3 lifts. You multiply them, you have potentially 9 lifts, but some of them don't compose. So the actual number is, I think the actual number is 5, and then 2 of them cancel each other to give you the 3 that you have on the right side.
All right, thanks.
That's how it's supposed to go. Okay, so just a slightly fancier example. Let's have this kind of crossing phenomenon, right, where we have 2 lines labeled, say 1, 2, and 2. And then as we emphasized, in that case, in the spectral network, there's going to be a third line. And you could ask, what is the, what do you do when you cross that third line? So I want to indicate that. So if I have a path P here, then among the detours that it can have, so it can have the usual kind of detours along the 2, 3 or the 1, 2, the same as I drew up above. But then you could ask, what happens when I cross this new 1, 3 line? Well, the 1, 3 always indicates to us that we're going to have a detour that starts on sheet 1 and ends on sheet 3. How is it going to do it? Well, what it does is it travels back to this intersection point. Then it takes the detour along here. So now it's on sheet 2. Then it takes the detour here. So now it's on sheet 3. Then it travels carefully back to where it hit the wall and then goes on like this. So that's a detour from 1 to 3. And in general, okay, hopefully from these 2 rules, you can kind of guess how you build up the detours more generally. Now, one remark about this one, we could have considered, again, another path P prime. And the comment is that, so f of P is supposed to be homotopic to f of P prime, right? And the remark is this wouldn't work without this extra detour. But if you look on the left, if you look at P prime, it does have a way of taking a detour from 1 to 3. Namely, it can take the 1, 2 first and then take the 2, 3. On the right, it can't do that because they come in the wrong order. So it has to compensate that by having this extra place where it can take a detour that goes from 1 to 3. So that's one way of explaining. At the end of the first talk, someone asked, well, why do you have to have these extra lines? So from the point of view of this path lifting procedure, this is why you need to have these extra lines. It's to ensure the homotopy invariance. Okay. Okay, so that's some procedure for taking paths on the base and lifting them to linear combinations of paths on the cover, using the extra kind of strut of this Stokes graph or spectral network. And so now the path lifting, this path lifting operation is sort of dual to a map from rank 1 local systems on sigma, almost local systems, to rank n local systems on C. So what do I mean by that? So given an almost local system, the almost local system, remember, means it's a local system except it has holonomy -1 around the branch points. That's why we had this -1 in the homotopy rule.
Structure on the surface.
Sorry?
Is it the same as just having spin structure on the surface?
It's not exactly the same as a spin structure. Okay, yeah, so the difference between a local system and an almost local system is the same as the difference between a spin structure on the base pulled back to the surface and a spin structure on the surface, right? If you take a spin structure on the base and pull it back to the surface, you do not get a spin structure on the surface. It's wrong by the same problem of a -1 around each. So the difference between those two, yeah, anyway, so it's related to spin structures, but it's not exactly the same thing as a spin structure. So okay, so now given almost local system A, rank 1, A over sigma, we can define an honest local system of rank n, L, and I'll write L is nab of A for non-abelianization, over C as follows. Well, it's almost tautological. So for an open set U inside of C, for an open set U inside of C, L, the space of sections of, well, let's see, I guess, strictly speaking, this is a local system that avoids the projection of the spectral network. Then the space of sections of the local system L on U is literally just the space of sections of A on the preimage of U. So it's the push forward in kind of the most obvious sense. But then for a path P from, let's say, open set U to U prime, so it begins in U and ends in U prime, the parallel transport from the space of sections over U to the space of sections over U prime is, well, you do the parallel transport upstairs. You do the parallel transport upstairs, but applied now to this formal linear combinations of paths, A of F of P. In other words, you just do A on each path and add them up. So in this way, you get a local system of rank n, which I guess a priori I only constructed it for you away from the spectral network, but I also gave you the parallel transport across the spectral network. And because it's homotopy invariant, this actually gives you a well-defined local system on the base. Okay, so this is a purely topological operation, like it's just some kind of cutting and pasting, if you like, that takes local systems over the cover to local systems on the base. And now the proposition is that that this procedure agrees with what we get from WKB. So I guess, well, the precise thing to say is that it's a proposition in cases where the WKB can be carried out rigorously. But in those cases, the local system L, which we considered downstairs, that we got as the space of sections of the space of solutions of this differential equation, and the A, which we considered upstairs, which we got by Borel resummation of the WKB series, they're related by exactly this procedure that I just told you, this kind of purely topological procedure. L is nab of A. And I guess I should be careful. I should include the dependence on the spectral network. So I'll call the spectral network W here. This nab operation depends on that. And the spectral network that we use in the exact WKB story is the one that came from choosing the phase argument of H bar and the tuple of differentials phi. Okay. Okay, so a corollary of that suppose P is a closed loop on C, just as a kind of practical corollary. Then a sort of practical thing you might like to compute is the trace of the holonomy around that loop. And the statement is that one way you can think of it is that your closed loop downstairs lifts to a bunch of closed loops on the cover. And so you get an expansion using this lifting rule. It comes to you as a sum of holonomies of the flat connection on the cover. So I'll remind you, X gamma was the notation we used last time for the holonomy around gamma of the loop A. Or I guess now also write just A of gamma. Holonomy around gamma of the local system A. So the trace of a holonomy downstairs is just a sum of the holonomies upstairs with some coefficients, which you compute by this path lifting procedure, depending on gamma and P. So these are some integers. So as a practical matter, you have some loop downstairs, you relate it to some combination of loops upstairs. And so in particular,
sorry, Andy.
So given we wrote a formula for the asymptotic expansion, so we have a formula. The asymptotic expansion of X gamma as H bar goes to 0. So through this procedure, that leads to the asymptotic expansion for the trace. Again, H bar goes to 0. Okay, and I should say again, of course, you know, these are theorems in kind of restricted, simple examples where everything's finite. And in general, they're conjectures. They're pretty concrete formulas in practice, which you can check. Okay. So that's what I mean about the kind of topology of this.
Sorry, Andy.
Yeah. Yeah, of course.
Why the
Sorry, I can't hear you.
Why the lifted path will be closed? Will be.
Right. Yeah, that's right. So the lift, of course, indeed, when you do the lift, you'll get some closed paths and some opens. But the idea is, if you want to compute the trace, then you throw away all the open ones and keep only the closed ones. So roughly, you know, the closed ones are like the diagonal entries with respect to some natural basis. The closed ones are the diagonal entries of the matrix. So you just keep the closed ones and throw away the open ones. But you're right that in general there are both open and closed ones. Did that answer the question?
Yeah.
Okay. Great. So, okay. So now I want to try to talk about the DT invariants. So what's our situation right now? So we've been describing a map. This non-abelianization map. And so far we thought of it as an operation that maps like an actual local system to an actual local system. But now let me just think of it on the level of the moduli space of objects. So on the level of moduli spaces, we could write it. So there's this nab sub W, but W depended on H bar and phi. So let me just write it like this: non-abelianization map depending on the data of H bar and phi, which was a map from a moduli space of almost flat GL1 connections over sigma to moduli space of flat GLN connections over C. And this map depends on H bar and phi, but it depends on them in this limited way. It only depends on the topology of the spectral network. So I should say the way this map depends on H bar and phi is only through the topology of W of argument of H bar and phi. So now, one of the key things about this this map, which again is proved in some limited cases and is a conjecture general, so I guess I write it as a conjecture, is that this map is a local symplectomorphism. And this is important. This is kind of an important conceptual thing in a lot of the applications. The idea is that this map on this moduli space, relating it to the much simpler symplectic structure on the moduli space of just GL1 connections. So when I say symplectomorphism, I should say symplectic form. Okay, so, you know, in cases where you can study the thing explicitly, you can check it, and it is a symplectomorphism. I think as of today, it's not officially a theorem, but now I'm describing for you, you know, just the kind of conceptual picture, so I'm not going to worry about that. So a consequence of that is that, you know, in particular, it's at least locally invertible, right? Being a symplectomorphism means in particular it's locally invertible. So we can think of inverting it to have, so now I'll call it the abelianization map, which goes the other way. Start from a GLN connection and map it to GL1 connection on the cover. And that in turn, you know, the moduli of these GL1 connections, as I say, that's a very simple thing. They're just described by their holonomies around a basis of loops. So this, you know, you think of as C star to the n with a standard simple symplectic structure. And so you think of this as giving like a local coordinate system on M of C GLN. And we said last time that in some examples, this recovers for you, known coordinate systems in the cluster structure. So this is a cluster coordinate system in examples, in some examples. So what is the picture that we have? We could think of it like this. We've got the parameter space of theta. Here I've got the parameter theta, which is the argument of H bar. Here we have the choice of a meromorphic quadratic differential. And in that space, we have a bunch of chambers. Maybe a picture looks something like this. We have a bunch of chambers where each chamber is a chamber where the topology of the spectral network does not change. Maybe there's other, so the picture, it actually looks a lot like the pictures that we draw on the curve, but now this is not a picture on the curve. This is a picture in the parameter space of quadratic differentials and angles. So each of these chambers is a place where the topology of the spectral network doesn't change. And when I cross one of these walls is where the topology of the spectral network is changing. So in each chamber, there's a kind of chamber decomposition. In each chamber, W theta of phi doesn't change topology. Just write what I said. And so as a consequence, this map, this coordinate system doesn't change. And then when we move from one chamber to another, there's some transformation of coordinates. So the coordinate systems that you're getting on the moduli of flat connections change when you move from one chamber to another. So each wall has attached to it.
Sorry, may I ask you a little thing?
Yeah.
So is it so that the spectral network is finite there, or
right? So same deal. So
Yeah.
This picture, again, in nice cases, this picture is going to be not everywhere dense.
So you're talking about the moduli spaces, but at most of the part, this is not very well defined. It's on some strata, special strata, yes? Or
I think not on strata.
Just.
Oh, sorry. Yeah, you mean, of course, that I haven't specified, for example, how I fix the order of the poles or something like that. So I agree. So to draw one of these pictures, what I should do is I should fix the orders of the poles of all the differentials, and then draw the picture holding those pole orders fixed. Then, having done that, you could ask, is the picture dense or not on that space of differentials? And then the answer, again, often in sort of complicated generic examples, the answer is that this picture will be dense. But in kind of simple baby examples, it's not dense.
Yeah.
Now, I actually believe that whether it's dense or not is actually not an essential problem. But to be sure, the things that have been proved are only proved in very baby examples.
Hi, Andy. Can I ask also ask a question? On this graph that you draw, is the base is like this phi arrow, so it's like a tuple of forms, and like it's like an infinite dimensional space, right? How do I understand this chamber structure? Like the base is like
yeah, same question. Yeah. So you should think of fixing the orders of the pole. So I agree. If I just say it's meromorphic and don't say anything else, then it's going to be a little painful to describe exactly what I mean here. But what you should think is that we fix at the beginning some choice of marked points on the surface, and we fix the orders of the poles that are allowed at each of those marked points. And after I do that, then this is a finite dimensional space.
Okay, thanks.
And C is fixed, yes, once and for all.
The Riemann surface, I think, although honestly, you could also vary the Riemann surface and you would have, everything I'm saying is actually still okay if you also vary the Riemann surface. Mm-hmm. But I was not thinking of doing that in drawing this picture. Okay, so each wall W is carrying some transformation of coordinates. So I'm saying in each chamber we have some coordinate system. So each wall is carrying a transformation from one coordinate system to another. So I'll write that transformation A sub W, and you can think of it, well, you think of it as a map from C star to the N to C star to the N, but the more canonical thing is to say it's an automorphism of this torus. It's an automorphism of this space of almost flat connections over the spectral cover, which is determined by the relation, if you like. How about here I write, well, let's draw a picture of it here. So here's W. On one side of the wall, I have the map AB. I'll just write it AB plus for the plus side of the wall. And on the other side of the wall, I have the map AB minus. That's AB H bar phi, when H bar and phi are on the two sides of the wall. And then I'm just saying that those two differ by some change of coordinates. Automorphism AB plus is AW composed with AB minus. So just some transformation of this torus C star to the N. So okay, let me draw an example. So again, I'm sorry, but I draw the always the most baby example. So I'll take C to be CP1, and I'll take my quadratic differentials. So I'm gonna be varying. I'm looking at a family of quadratic differentials on CP1. So this is n equals 2, and then my quadratic differential I'll take to be of the form cubic, like I drew before, but this time I'll include a linear term. So z cubed plus z plus u dz squared. And then I'll let u be like I epsilon plus the real part of u. So imagine you fix a kind of small imaginary part and vary the real part. Then the picture looks like this. So here's theta going from 0 to pi. And here's the real part of u. And then the picture of the chambers is like this. There are, I should draw this. Well, that's okay. That's a picture of what the chamber structure looked in that case. So each one of these walls has some meaning, right? Each of these walls describes a moment where the topology of the spectral network suddenly changes. So let me say a little more concretely what they are in, or what kind of thing they are in this case. So the question now is, what are these automorphisms? What are these changes of coordinates? What are the A sub W? So the most basic example, I showed you a picture of before, but now let me paste it in. So the most basic example is a phenomenon like this. So remember, when the moment when we reach one of these walls in the parameter space is supposed to be a moment when the topology of the spectral network suddenly changes. And so one thing that's convenient to do is to fix a particular point, all right, phi in the base, and just vary the phase and see how the topology changes as you vary the phase. So in this simple example, what we'll see is as we vary the phase with this particular cubic differential, with this particular quadratic differential given by a cubic polynomial, what we'll see is that exactly twice as we vary the phase, there will appear one of these saddle connections, a trajectory that goes directly from one 0 of the polynomial to another. For example, I guess I can even draw it when, so what it'll look like concretely for like a small value of real part of u in this example is it'll look something like this. We have the 3 zeros like this, and then at one phase, there will appear a saddle connection here. And at another phase, there will appear a saddle connection here. And those two phases correspond to the two changes of chamber that I have here as I vary the phase. So maybe I'll move that up here. Sorry. Okay, that's not worth it. So anyway, so one of the kinds of topology change that you get as you move around in the parameter space is this kind of topology change that comes from a saddle connection. So just a little bit about that object. So let the charge of the saddle connection be the cycle gamma in the first homology of the spectral curve, be that cycle shown in the figure. So anytime I have a saddle connection, it has a corresponding cycle on the spectral curve. And then one thing you can check is that the phase at which it appears is not a random phase, but rather it's the argument of the period. The period introduced before is just the integral of the tautological one form. So these things appear, if they appear at a very specific place. And then the automorphism in this case, A sub W is, so it's just some automorphism of the of this torus of abelian connections. So concretely, I could describe it by saying, how does it transform the holonomies of the abelian connection? And it transforms them just by the following rule. The holonomy x mu gets transformed to x mu times 1 minus x gamma, so gamma, the charge of the saddle connection, this loop that I drew here, to the power of the intersection number between mu and gamma. And this transformation law has been known in many other contexts. So in exact WKB, this transformation law has certainly been written down before. In the context that it came up here, it was written down by, well, in some closely related contexts, it was written down by Kontsevich-Soibelman, and also it's essentially a cluster transformation of Fock and Goncharov, as I say, also known to the exact WKB community. Anyway, this is the formula. This is kind of the key formula, this automorphism of this kind of universal automorphism of the torus, which is associated in this business to the saddle connection. Now, that can happen for n equals 2. You can also have very much the same picture for higher n, but then in higher n, you can also have new things. So here's the simplest example of a new thing that happens for higher n. So here again, I have, I'm holding my differentials fixed and just varying the phase. And again, the topology of the picture doesn't change. And then there's one critical moment where the topology of the picture changes. It's associated now with the appearance of this kind of trivalent tree here. This tree. And that tree, just like for the saddle connection, that tree has a kind of canonical way of lifting it up to the cover. That's the gamma that I've shown here. Now it involves 3 sheets of the covering going around. And so here too, you can just calculate directly what's the automorphism, what's the transformation of coordinates that comes from changing topology from one to the other. And then you again, for this kind of object, you get AW equals K gamma, exactly the same automorphism that I wrote above. So in other words, in this game, these trivalent trees count exactly the same as saddle connections. And I want to say that they're a kind of higher rank analog of a higher rank object, which should be thought of as kind of a higher rank version of a saddle connection. Okay. And so again, here, these are kind of cluster transformations.
Is there a statement that we always get something like that?
For a tree. So you can, so similarly for any tree, meaning, you know, we could have drawn a more complicated object, like we could have drawn something like this, involving 4 branch points, and maybe I'll draw it in purple because it's the analog of the purple thing above. So you could have had some picture like this. So then again, there's a cycle. There's a cycle on the spectral curve. And again, so if you have a critical phase where this tree appears, then again, you'll get AW equals that same Kontsevich-Soibelman automorphism. But the thing is, the trees are not the only thing in the game. So if it was only trees, somehow life would be pretty easy. But even in the case of quadratic differentials, there's more than just the trees, even in the n equals 2 case. So one other example. So here I don't have a picture of it because it's somehow harder to make a picture. Well, I can make a picture of what happens at the critical phase, I guess. So let's say again, for now, back to n equals 2. So we can have a phase theta c at which, yeah, we can draw this. So at which W of phi and theta c includes a picture like this. And this doesn't happen for like polynomial differentials in the plane, but it can happen as soon as you have some more interesting topology. You can get a thing like this, where you have like a closed loop. And then when you have it, you always have another closed loop like this. So you have this kind of ring domain that's foliated by leaves of my foliation. So there can be some critical phase where a ring domain like that appears. Then again, you can ask, okay, what's the transformation of coordinates on the 2 sides of the place where the ring domain appears? And then the answer is, so at such a wall, we get a transformation which is a lot like this Kontsevich-Soibelman transformation. So again, there's a charge associated with it, gamma, which I could represent just by lifting this guy. You actually lift it to both sheets with opposite orientations. So there's a canonical gamma again. But the automorphism that you get in this case is not the simple one that I wrote before. It's that one to the power -2. In other words, we map x mu to x mu times 1 minus x gamma. Before it was to the power of the intersection number. Now it's to the power -2 times the intersection number. So this is not a cluster transformation for those who are interested in clusters. But on the other hand, it plays in this theory very much the same role as a cluster transformation. And so in the story of triangulations of surfaces, the way that you reach this thing is you first do an infinite number of flips of triangulations. then you arrive at this critical phase. You do this transformation, and then you do another infinite sequence of flips. That's how you get from one finite chamber to another. Anyway, so there are things like that.
May I ask one little thing? So do
do
you allow density domains at all in your quadratic differentials?
Right. So for the part of the story where we have, where there are rigorous theorems, then you always set it up so that doesn't happen. So you set it up so that there's a pole of at least order 2 somewhere on the surface, and then you make things generic enough so that you never get like dense trajectories. Now, recently people have developed some of the theory that I need here, that we would need for this story, even in the case of dense trajectories. So in particular, maybe I won't get to mention them later, so I'll mention them now. There's Aaron Finyas, and also on the categorical side, there's very recently Fabian Hayden. But everything I'm saying, so most of it is not rigorous in the case where you have this dense trajectories. But nevertheless, the formal structure seems to be exactly the same. For example, in numerical experiments and so on, you can see the formal structure is exactly the same. Okay. So, all right. So our picture is that we have, we have this chamber decomposition of our parameter space with, maybe it's complicated, with a bunch of walls. And on each wall, we have this automorphism, A sub W, automorphism of the torus. And now I want to sort of organize those automorphisms a little bit into just a collection of numbers. So let's make a definition. So let me fix a phi, which is a little bit generic. I want to fix it so that the periods are all linearly independent, except when they can't be. So that means that the periods for linearly independent cycles are linearly independent. Sorry, what do I mean by linearly independent for the periods? I mean they don't have the same phase. They're independent over R. So they have the same phase only if the homology classes are multiples of each other. So that's what happens generically in this picture, but it doesn't happen, for example, here at the place where the walls touch. So let's avoid that situation. And then for each wall W at phi, so for example, maybe I fix this phi, and I look now just at the walls over that phi. So just this discrete set of points here. Each one of them is lying on some wall. So for each one of those walls, so I have the attached automorphism, change of coordinates. And then I'll define numbers omega of gamma phi by expanding this automorphism AW as a product over all the gammas associated to that wall. What is gamma associated to that wall? They're just all the homology classes such that the period is equal to the argument of Z gamma is equal to theta, or the argument of H bar. So for each one of these walls, there's some collection of homology classes that are kind of attached to that wall. Like for the saddle connection, the homology class attached was the class gamma that I drew. So in general, the automorphism that you get is a product over all the charges supported at that wall of these automorphisms K gamma appearing to some power, omega of gamma. And I'll call that power omega of gamma. So in the examples above, we saw cases where omega equaled 1 and omega equaled -2. But in general, whatever powers appear there, I'll just call them omega of gamma. Just define that number. And then, so whenever you have some kind of degeneration of the spectral network, there's an algorithm for computing these numbers. But it's in general a hard algorithm, but it's a completely, you can do it on a computer for computing the omega of gamma from the topology of W of theta phi at the walls. So in other words, for any phi, now I've produced a bunch of numbers. I've told you how to produce a bunch of numbers by drawing all the spectral networks, looking at how the topology jumps from place to place. And then for each jump, there's some collection of numbers attached. Now then, and there's a conjecture in DT theory, which is also a conjecture here, which is that these numbers are actually integers, always integers. So we saw it in the example that we drew. Of course, they were integers. In fact, in physics, we expect even more. We expect they should be the dimensions of some vector spaces, not only integers, but at least they should be integers. Well, index dimension. Dimensions up to a sign. So, okay, so concretely, so for example, what we're saying is,
whether this numbers can be considered as zeta function. The kind of a zeta
I couldn't hear that so well.
So, sorry, there is a problem with. Sorry. Whether these numbers can be considered as a kind of a zeta function.
As a zeta function?
Yeah.
I don't know. That's a very interesting. I have no comment about that. I'd like to hear more about the reason for the suggestion. I know that Tom Manero once tried to do that and didn't succeed, but yeah. So in short, I don't know. But so just for an example, so when n is 2, these integers are really kind of counting invariants. So they're the number of saddle connections for the differential phi 2 rotated by any phase with charge gamma minus 2 times the number of phi ring domains with charge gamma. And so for higher n, these invariants are counting in a similar way these more complicated objects, like for example, the tree that I drew for you. Okay, so that's the kind of thing that they are.
Are there any relations between omegas?
Relations between the omegas?
Yes.
For a fixed phi.
Yes.
In a certain sense there are. So it's true that, for example, if you look at a single phi and you build a generating function. So imagine you do the following thing. You fix a phi, you fix a gamma, and you build a generating function of all the omegas that are multiples of that gamma. Now, in our simple examples here, that generating function would just be a polynomial. It wouldn't be very interesting. But in fancier examples, that generating function can be some interesting series. And then it is a true fact that that series actually, in many examples, and I think probably always, that series actually obeys an algebraic equation. This kind of thing has been conjectured pretty generally in DT theory. And in these examples that come from spectral networks, you can see that it's true. So there are some relations like that. Okay, so in short, yes, it does seem that there are some relations among them.
Okay.
There's another kind of relation which relates the omegas at different values of phi. Let me just say a word about that. So let me copy the picture that I had above. So we had this picture here. So that's a picture of the chamber structure in this kind of simplest example of the story, simplest non-trivial example. And so here, now each one of these walls is labeled by one of the saddle connections. It has a corresponding charge. So for example, let me label this one gamma 1, this one gamma 2, then this one is gamma 1 plus gamma 2. So this is gamma 2, this is gamma 1, and so on. So now, so here, we have the situation for small part of U. We have omega of gamma 1 and phi 2 equals 1. Omega of gamma 2 and phi 2 equals to 1. But there's no wall corresponding to gamma 1 plus gamma 2. That invariant equals 0. On the other hand, for large values of real part of U, the invariants are different, right? So this is the same, but now omega of gamma 1 plus gamma 2 and phi 2 is also equal to 1. We have these 3 saddle connections instead of 2 on this side. Then you could ask, is it possible to deduce one from the other? If you know the structure in one chamber, in one region, is it possible to figure out the structure in another region? And the answer to that is yes. Because, well, one way to understand it is you can do the following thing. You say, each of these chambers corresponds to some coordinate system. Well, I can do the following thing. I pick 2 points, say these 2 points. And now I go from one to the other along, say, this path. Or I can go along this path. Now, along those 2 different paths, I'm meeting 2 different sequences of coordinate transformations, right? So at each wall, I have a coordinate transformation associated with that wall. In one case, in the first case, what I get is, when I go along this path on the left, what I get is k gamma 1, k gamma 2. When I go along this path that goes up first and then across. If I go along the other path, I get k gamma 2, k gamma 1 plus gamma 2, k gamma 1. So now there's a kind of non-trivial algebraic fact, which is that if you really compose those automorphisms carefully, if you compose the 2 on the left, it's equal to the composition of the 3 on the right. Okay, so in the cluster world, I think this is known from many different points of view, so it's called the pentagon identity. But in this context, one way you can think of it is that it's an instance of a kind of wall crossing formula for these invariants, omega of gamma and phi 2. And what I mean by that is, if I knew the spectrum on the left, if I knew that there's gamma 1 and gamma 2 on the left, and then I ask, what will be the invariants that appear on the right? Knowing a priori only what order they have to come in, that the gamma 2 one has to come before the gamma 1, and if there are any in between, they'll come in order dictated by the phases of the z gammas. Just knowing what ordering they have to come in is sufficient to completely determine the exponents that appear here. In this case, the exponent 1 appears just for gamma 2, gamma 1 plus gamma 2, and gamma 1, and no others. So that's an instance of a more general thing called the Kontsevich-Soibelman wall crossing formula. If you have a collection of invariants that transforms in this way, that's called the Kontsevich-Soibelman wall crossing formula. Okay, and so the expectation is that very generally, even in these higher rank examples, you're going to have exactly the same formal structure. You have coordinate systems and transformation laws. And so the invariants that we define in the higher rank situation will again have this kind of wall crossing property that you can determine them at one point of the parameter space. You can determine them at any point, knowing them at one point by using this kind of trick. Okay. So in that sense, there's relations among them. There's relations between the invariants at different gammas, at different phis. Now, this Kontsevich-Stolboven formula, what was their original context? Their original context was the theory of Donaldson-Thomas invariants. And so let me say that this is not a coincidence. Okay, so now I can tell you something that really is a theorem. So when n equals 2. So let's, and this is a theorem due to Bridgeland and Smith. Okay, and this involves sort of slightly heavier technology than the rest of what I'm saying, but nevertheless, it's nice to know that there is such a theorem. So, so let's fix a topological surface, say S, with marked points, pi. So I think I'm probably stating this theorem slightly imprecisely. So this is a rough statement of the theorem. So fix a topological surface with marked points pi, labeled by integers ni, so one for each marked point, with at least one ni greater than or equal to 2. The statement is that given that data exists a category, a triangulated 3-Calabi-Yau category, such that for each choice of a complex structure on the surface and a meromorphic quadratic differential phi 2 on on S with that complex structure, such that phi 2 has poles only at the ni and only of orders pi, poles at, sorry, I said it backwards, poles at the points pi of order ni. So we're studying just moduli of complex surfaces with the meromorphic differentials with poles of fixed order, and for each one of those, for each choice of that data, you get a stability condition on the category. Okay, actually more than one, but let's just take any one of them. Some discrete set of possible stability conditions. Take any one of them. So category C. So our geometric data, in other words, the data we've been using in our story, gets translated to a category plus a stability condition. And once you have a category stability condition, there's this algebrogeometric thing invented by Kontsevich-Stolboven, which is you can construct the generalized Donaldson-Thomas invariants. They're counting objects of that category in an appropriate sense. And the statement is that the numbers which we defined as counting saddle connections and closed trajectories have this kind of more abstract meaning, that they are the generalized Donaldson-Thomas invariants associated to C with this stability condition. So the story is you have a category, you sort of want to count all the stable objects of the category in an appropriate sense. You need some notion of what's a stable object. That's the stability condition. And so our data gives you exactly what you need to set up that problem. And according to Bridgeland Smith, the invariants that we discussed above actually are exactly generalized Donaldson-Thomas invariants. So then from that point of view, this wall crossing formula, which I wanted to describe it as a consequence of the existence of these coordinate systems, but it also just follows from the abstract machinery of Kontsevich-Soibelman that that they should obey the wall crossing formula.
Does it imply that all omegas are integers?
Oh, good question. I mean, in this case, you know it. In this specific case, you know it just because you have an explicit formula. I think that in general, if I only gave you, okay, maybe some expert will know better, but my understanding of it is that today, if someone gives me a triangulated 3-Calabi-Yau category and a stability condition, and they don't give me any other information, that the Kontsevich-Soibelman machine, well, maybe you also need some orientation data. Suppose you have also the orientation data. Then the Kontsevich-Soibelman machine will give you some numbers, but it's not known that they're integers. In the totally abstract world of Kontsevich-Soibelman, I think that's still a conjecture.
Okay.
Andrew, and when you speak, when you speak about Donaldson-Thomas invariants, are these invariants of the projective plane?
Of what?
Of the projective plane, or what?
Oh, so these are these. It's no, unfortunately, it's not literally Donaldson-Thomas. It's generalized Donaldson-Thomas. So it's, I mean, if you want to say what's the geometric object that they're associated to, it's the, I think the thing I understand best is that it has to do with the Fukaya category of a Calabi-Yau threefold that you build by taking a ADE fibration for your over your Riemann surface. So it's not directly associated to, like, you know, at least the way I understand it, it's not directly associated to like counting sheaves on some algebraic variety. It's rather associated to this category, which comes to you most naturally as the Fukaya category of symplectic space.
Okay.
Well, Bridgel and Smith didn't construct it that way. They constructed it a totally algebraic way. There's a later paper by Smith who explained the Fukaya category interpretation of it. And I should say, very important, very recently, so this is Bridgel and Smith's theorem, which is now a few years old. But very recently, there's a theorem by Fabian Hayden, which says that the same thing works without the poles. So here's a case where you actually can do something with the dense trajectories and so on. And so in particular, you could define the invariants the same way, even without the poles. And a consequence of this theorem is that they still obey the wall crossing formula. Then you can ask, what are the cluster coordinates in that case? And that's part of what Aaron Fenya has partially constructed. But now we don't need them to just prove the wall crossing formula because Hayden has proved it. Okay. So, all right, so I explained to you, I described these DT invariants. So now the idea is that for higher rank, the spectral networks are producing more examples of, you know, DT type invariants, which it would be very nice to find a category and prove the analog of this theorem of Bridgel and Smith in the higher rank case. And that hasn't been done. Okay. Well, there's more I wanted to say, which is in the notes, but I've reached the end of the time, and this is actually a reasonable stopping place in the sense that I completely finished the DT invariants and didn't start on anything else. So, so maybe this is actually a good place to stop.
Okay, so you want to stop?
Well, I think I should. I've gone for the time that was allotted. It's, if you're interested in more, it is in these notes. But
like, if you want to say something more, so I think we have like plus 10 minutes. So if you,
I can. Well, all right. I'll say one more thing then. So what's one of the applications of this? Yeah, I won't get to the hyperkähler geometry, but let me say something that's preliminary to it, which is this Riemann-Hilbert problem. So remember, we had this family of local systems like Schrodinger equations that we wanted to solve that came from the data of a surface with a differential. So we have these systems that we want to understand. And by exact WKB, we formulated the abelianization of it, these GL1 local systems with holonomy functions. I wrote them as X gamma of H bar. And the idea is that these, in simple examples, are like the cluster coordinates of the original L. So you could ask, how can I determine these functions? And so one thing I told you is that they come by Borel resummation of some series. There's another way of getting your hands on these functions, which at least for me is easier. So these functions, if you look at all the properties that we proposed for them, you find the following. So they're functions of H bar, which as H bar goes to 0, they have an asymptotic expansion, which you could write down, but in particular, the lead here is just the exponential of the period divided by H bar. And then this X gamma of H bar is not an analytic function of H bar, it's piecewise analytic. It jumps when we hit those walls that we were talking about before. So if I look at it in the H bar plane, I'll see a picture where walls now are just at some fixed phases of H bar. So for example, the most symmetric example is this, this cubic example in n equals 2. So there we just had 6 walls labeled like this. So each one has an automorphism attached to it, which in this case are just those simple automorphisms that the cluster moves. So it's piecewise analytic, but it jumps by some specific automorphism A2 at each wall W. So here we have 6. Well, this is the example of phi 2 is z cubed minus 1 dz squared. The picture would be like this. And the last thing is that X gamma of H bar has a kind of moderate growth. This is a thing that's true in examples, but one doesn't know exactly how to prove in general. For example, in this case, it'll have no growth at all. In this example, it'll just approach a constant at large H bar. Anyway, so the function, if you assemble together all the things we think about this function, it should have these properties, and then you could hope that those properties are actually enough to determine the function. So this is still part of the conjecture, is that these properties are actually sufficient to characterize the function X gamma of H bar. If that's true, that's kind of neat because it's a way of finding the monodromy of the differential equation, which has nothing to do with actually integrating the equation. It only uses the data of these automorphisms and the periods and nothing else. And experimentally, you can try to do this, and this is connected to things that have been known in the in special cases. This has been known in the physics literature in a totally different language. This is something called the ODEIM correspondence. Anyway, so that's the conjecture which you can formulate, and then you can test it. And so let me show you one example of a test of this conjecture. I'll just paste you one more picture. But yeah, so I want to emphasize, so I and David Dumas did a bunch of numerical tests of this, but we're certainly not the first ones to study closely related things. So here's a picture. So this is for the case, this is for a slightly fancier case. This is for the cubic, this is for n equals 3 with the differential phi 3. So phi 2 is 0, phi direct differential 0, and phi 3 we took to be this cubic polynomial, dz cubed. And here's the data. So in this case, there's the spectral curve has homology of rank 4. So there's 4 independent colored lines here for the 4 cluster coordinates, or the 4 kind of basis elements. And what we did is we computed them using this kind of, using just their asymptotics. You can formulate some, using just their asymptotics and jumps, you formulate some integral equation which they should satisfy. Then on the one hand, you solve the integral equation. On the other hand, you just numerically integrate the equation. In this case, it's a, it's a higher rank equation. And you compare them, and you see that the results match extremely well. So here on this plot, you see kind of little stars, but that star is actually the superimposition of a plus and a cross, which are from the 2 methods of computing. So that's a kind of test of, many of the conjectures altogether somehow. Only if all of them are true do you expect this to work. So at least in this sample, everything seems to be hanging together okay. Okay, so now I think I'll stop. And if you want to see the hyperkähler stuff, that's in the notes.
Okay, let's thank Andy for great lectures, for all 3 of them.
Thanks a lot. This was a lot of fun.
Thank you. But yeah, while people thinking about questions, so may I just ask, like, general, can you formulate, well, what are interesting question to think about? And
there are a lot of hard questions. See, the thing is, I mean, I mentioned various things which are conjectures, right? And so any one of them, it would be fantastic to prove it. There's one thing, okay, there's one thing which I think is interesting, and somehow elementary, but which is, so like in this example, for instance, we had a cubic differential, which is polynomial of degree 3, and the quadratic differential, which is 0. You can do a similar thing where you turn on the quadratic differential. And this one was related to the cluster structure on GR36, in the sense that the moduli space of decorated local systems we encounter in this case is this quotient of GR36. And so these functions are cluster coordinates on for some seed on GR36. Now, as an experimental effect, when you draw the spectral network in this case, it is nice and finite. But I don't have a theoretical understanding of why it's finite. And more than that, the expectation, I think, would be that if I had done something similar, so imagine I'd taken a polynomial phi3, which is polynomial of degree k. Then I'm supposed to encounter something that has to do with GR3, I guess, k plus 3. And the cluster structure on GR3 k plus 3 behaves very differently, right? Depending on whether k is less than or equal to 5 or bigger than 5. So what I would kind of expect is that when you actually carry out this algorithm to draw the spectral network, what you find is that everything is kind of nice and finite up to polynomial degree 5. And then after degree 5, something lets loose, and it becomes possible to have kind of infinitely many walls generated. So roughly for small enough degree, what happens is that everyone goes to infinity fast enough that they can't make too much trouble before they get there. But somehow for a polynomial of high enough degree, it should be different. There should be some kind of infinite structure that appears, and which is related to the fact that the cluster algebra, GR3 9 or something, is not of finite type anymore. So that seems like a cool kind of elementary question in a sense. I mean, it's just something that you just draw these trajectories. I'm not aware of anyone has investigated this question. I mean, there is certainly a little bit of literature in the exact WKB world about this kind of phenomenon, but but as far as I know, they haven't investigated this, and I think that's a cool question, which would be fun to understand.
Wow, works for me. At least I'm able to.
Oh, maybe Boris knows.
Well, I have a comment. I think I studied those things, and even for high order. it's important. I know how to draw pictures if you have, you know, a polynomial of the same degree as the differential. They come out very, very interesting trees in the plane. Maybe I can show you.
So you're saying if I would take like 5,4 as z to the fourth plus lower order stuff, dz to the fourth, exactly in that case you did it. Oh, very interesting. I certainly,
for the whole
I would love to know about that.
There is an interesting interpretation and so on. Yeah.
Great, great.
I have a question also.
Yes.
You have mentioned you are measuring some periods along some given basis, yeah, in the first homology.
I can't hear you super well. I'm sorry.
Sorry, today it's some problem with you're measuring, you're integrating something along a basis in homology.
Oh, yes.
How do you choose this basis?
Right.
Basis.
Right. So the first thing is all the statements, the way I formulated it, are basis independent. So you don't need, I just choose any basis. It's true, right, that in the cluster world, there are some bases that are preferred, right? You know, when you have the seed, it comes with a basis. And I don't know, except in the simple cases, the triangulations of surfaces, I don't know a general algorithm for producing that basis. So, I mean, I know how to produce the X gammas for an arbitrary cycle gamma, but I don't know how to pick out, you know, what's the favorite basis that will correspond to the actual cluster variables. But in general, you know, if I didn't know about clusters, I would have thought that there's no need for any basis. I would have just said, well, you know, the whole thing is basis and I don't care. But of course, in the cluster world, it is important to have this particular basis. So yeah, that I don't understand very well. That's one, well, one of many things.
I think I also have a question. Maybe it's a little vague. So you explained about this BPS counting, and I understand that kind of on one hand that counts some BPS states, which are certain representations. On the other, it should be counting some, you know, points or visual curves. I always fail to understand how the two are related. Do you think you could say a few words about it?
How they're supposed to be related? I mean, the kind of rough answer. Okay, so I mean, this of course will be a physics answer, but I mean, if I think of this category, so we said it's a DT invariance of some category, right? And that category I could think of as being the Fukaya category of some Calabi fold. Let me call it Y. So this is Smith and Bridgeland Smith's description in this one case, but it's also what you expect from physics. So so the DT invariance for C, oh great. So in this case, the stability condition corresponds to a complex structure on Y. So moduli space, and you choose a point in this moduli space. And in that case, the DT invariance for C, how you're supposed to think of the DT invariance is that they're counting special Lagrangian 3 cycles inside of Y. Now, let me quickly draw the picture of that special Lagrangian 3 cycle.
And what do you mean?
Then I'll try to say, I mean, literally, so special submanifold of dimension 3. So so Y is a Calabi-Yau 3-fold. So the real dimension of Y is 6, and so it has it's a Calabi-Yau, so it could have special Lagrangian 3 cycles inside of it, and so that's what I mean. So the picture of them, this Calabi-Yau is fibered over C. Okay, so here's C, and now Y fibering over C. So the fiber is a 4-dimensional guy which has, well, we could write the equation. So since we're in the case of degree 2, we can write the equation. It just looks like this. Sorry, did I write it right? I don't want that z squared. Yeah, here's one equation in 4 variables. So locally, this is what the thing looks like. And so the fiber over a generic point, there's a kind of, roughly speaking, a kind of volume minimizing sphere in the fiber, whose size is controlled by this phi 2 of z. And so what the thing looks like is you have this sphere which collapses at the 2 ends of the interval. So we have like, so it's like a 3 sphere, which is fibered over an interval, and the generic fiber is a 2 sphere. So the picture is that when you have one of these special trajectories downstairs, that's supposed to lift to something which is approximately a special Lagrangian 3 cycle in Y. Okay, now I didn't tell you yet why that's the same as a BPS state. But once we've gotten this far, now we can say that if we study string theory, type 2B string theory, on this threefold Y, one of the ways you get particles in that theory is to take these objects which are called D3 branes. So it's a thing which has it has total dimension 4. But we could take 3 of the dimensions to be kind of wrapped over the special Lagrangian, and then the 4th dimension is just so this is L cross R inside of Y cross R4. So what you see in the remaining R4 is just 1 dimension, which is like the trajectory of a particle. So this is just a general thing about why DT invariants that count special Lagrangians have something to do with particles. Yeah, okay, I don't know if that was helpful, but that's...
What would be, no, it actually was, but what would be a good reference for this story, if any?
Oh, for how you get BPS particles by wrapping D-branes over... Yeah, so this is a pretty old statement. There's statements very much like this in papers by yeah, I think this is probably contained in paper of Clem, Lersch, Meyer, Waffe. I think I have that right. There's an old paper where, in fact, they were studying more or less the same thing that I'm describing here in the case of a quadratic differential. Oh, good, send a correct link. So yeah, in fact, I think in that paper they're explaining very specifically why exactly the trajectories that I drew here. Oh, Klimler's Waffe Warner, thank you. They're explaining why exactly these trajectories that I drew are supposed to correspond to BPS states. Yeah, so that's probably a good reference for that. Yeah.
And also kind of follow-up question, is that right that this recipe for writing this DT invariant, I forget what's called, right? Well, because for counting DT invariants, so it's basically answered in this Gonchov and Shen paper for GLM case. So that just gives you a complete answer. Right.
So that should be the same object. Yeah.
Mm-hmm. Okay. Thank you.
I think that's right. I hadn't actually thought of that, but I guess you're right that what I would be saying is that there's a sort of interpretation of the invariant that they defined in terms of counting these trees and so on. But that's right. They have a kind of formula for the invariant.
All right. Thank you. Thanks.
Well, if you run out of questions, let's thank Andrew again. And yeah, thanks for great talks.
Thanks. It was a lot of fun.
Okay. Well. I think we
see you.
Yeah, see you around.
See you in person next time, I hope.